Okay, so I think we can start today's webinar. So welcome everybody, and thank you for being here today attending this webinar. I am Giacomo Mezzetti on behalf of ETA. We are leading the communication, dissemination, and exploitation part in the M²ARE project. Today we will host like two speakers, Henrik Schlosser from Air Liquide Research and Development, and Michael Bampu from CERT. The title of this webinar is Mapping the Availability, Location, and Quality of Bio-CO2 Streams in Europe. So just a few things before starting the webinar. It will be recorded and put on YouTube channel after it will be finished. And the presentation, all the two presentations will be available on the website. And please just a quick recommendation about to use the Q&A for the questions and not the chat box. Use the chat box just for greetings and communication. So during the webinar, I'll provide like also a few useful links if needed. And so it's everything from my side. So I think that Henrik Schlosser can start with its presentation with the introduction of the M²ARE project. So please, Henrik, the floor is yours.
Thank you very much, Giacomo, and welcome all of you. I'm very pleased to welcome so many of you, and I think it's a very interesting topic today. As the availability of the feedstock for novel biofuels is, of course, very important. Just before we dive deep into the European biogenic CO2 sources, I would like to present to you the framework of the study, which is a EU-funded project called M²ARE. M²ARE is about maritime methanol, with the goal of developing an adaptable, renewable, and environmentally friendly process for the production of renewable maritime fuels. So, like all of the industries, the global shipping industry faces a huge challenge to decarbonize in the upcoming years. So therefore, the industry committed to some ambitious targets that are, of course, in line with the current EU regulations. So by 2030, already a reduction of about 20% of the total greenhouse gases shall be achieved. And then the industry pledged to be carbon neutral by 2050. And of course, this creates a huge demand for renewable fuels that replace existing fuels that are based on fossil resources. And here by 2050, it is estimated that a total of 220 million tons of fuels per year are needed, which of course creates a huge market for these novel fuels, but also requires the availability of new feedstocks, which are renewable. And we believe that methanol can play a key role here as one of the fuels to be used in the future. So methanol is a relatively simple molecule, of course, and it has the advantage that it's has a much lower environmental risk compared to conventional fuels, so heavy fuel oils or diesel, for example. And also by switching to methanol, actually up to 80% of CO2 emissions can be saved. And currently, we see a stark rise in the interest in methanol. So just 3 years ago in 2021, there were less than 20 ships on order that are capable of running on methanol, while now there are over 200 ships on order and able to run in the coming years on methanol. But of course, one of the major challenges for methanol as a maritime fuel is its price, and especially for renewable methanol, of course. And so there, we think M²ARE comes into play. So we want to reduce the cost following this approach. So we have partners along the whole value chain. So starting from the feedstocks all the way to the final products. And we look also then, of course, at the whole value chain, starting from renewable hydrogen, coming from, for example, water electrolysis. And then, of course, the carbon source in this case is biogenic CO2, so that at the end, the methanol is also considered renewable. And there, of course, we will focus on today on this webinar. But once we combine these two feedstocks, of course, we can produce methanol from CO2 and hydrogen. And there we use an existing pilot plant here at the R&D facilities of Air Liquide to demonstrate the production of methanol. For several thousand hours, we will run the plant to produce methanol, to investigate the process, but also to optimize, of course, the process. But we will not stop there. We also want to improve upon the process itself. And so therefore, we develop a new reactor concept for which we believe we can lower the final cost of the methanol. Also, after the reaction of CO2 and hydrogen to methanol, you also get water as a byproduct. Also some other higher alcohols, for example, as byproduct. And to then purify the crude methanol to the final maritime methanol, we want to develop a new simplified purification. So to be able to just in one step produce a tailor-made fuel that can be used directly in the engines of the ships. And there to test this purification system, specifically our partner M2ARE will perform some engine tests. So to test the performance of the engines, properties of the exhaust, also look at the engine equipment like the injection systems, to really gauge the feasibility of these new tailor-made fuels, for which we hope to reduce overall cost. And then lastly, of course, the whole project is underlined by a strong focus on life cycle assessments and techno-economic analysis to be able to compare the process to other renewable fuels, for example. And of course, to be able to scale up this technology. So by the end of the project, which is the mid of 2027, we want to be able to have the first commercial offers for this project. And so without further ado, I want to leave the floor to Michael for then the in-depth presentation on the biogenic CO2 sources in Europe.
Hello, also from my side. Thanks a lot, Henrik and Giacomo, for the introduction and the very interesting presentations. So, starting now with the mapping of bio-CO2 sources across Europe for the production of maritime methanol, what we are going to discuss today is what is actually out there in terms of bio-CO2 sources, which aspects matter regarding the production of methanol synthesis using this bio-CO2. Myself, I'm Michael Babao. I'm a collaborating researcher at the Artemis Laboratory of the Chemical Process and Energy Resources Institute in the Center for Research and Technology Hellas, which is a research institute located in Greece. Starting now with a brief introduction. So, as also Henrik mentioned previously,
Michael, maybe you can switch to the presentation mode.
Okay.
Yeah, swap presenter view.
Now?
Yes,
Yeah, great.
perfect.
Thank you.
Thank you.
Great. Okay, what's the goal regarding the maritime industry is to at least a 50% decrease the total annual GHG emissions. So the scope of the M2ARE project is to use bio-CO2 in conjunction with renewable hydrogen to produce methanol that could be eventually used in ships. So why biogenic CO2? Because this bio-CO2 is in the natural carbon cycle, so we will not add additional stress to the carbon cycle. On the contrary to fossil CO2, which adds additional stress to the carbon cycle. So having this in mind, here you can see an overview of the bio-CO2 value chain to methanol synthesis. So if we can say we have 4 different sections here, we have the bio-CO2 section, in which we are going to focus today, which is about the bio-CO2 emissions, the capture, the cleaning, storage, and then the transportation of the CO2. Then, of course, we have the production of hydrogen using renewable energy sources, the synthesis of methanol incorporating renewable hydrogen and bio-CO2, and also, finally, the utilization of methanol in ships. So the port would be, let's say, the end user that is going to be to use this methanol synthesis. So the vessels that are located in the port. So which are the 3 main biomass conversion processes that are generating bio-CO2 mainly as a byproduct? So we have 3 here. We have the combustion, we have the digestion, and fermentation. So the combustion process involves the combustion of the feedstock to produce heat, electricity, or combined heat and power. So there are different solutions to this application. They could range from domestic heating up to district heating and large-scale power generation. But usually the streams that are the bio-CO2 streams from the combustion process involve low CO2 contents, lower than 50%. They have high inert contents like oxygen, NOx, SOx, and other traces that are also related to the process and the feedstock. The combustion process is the main emission source in the biomass power plant sector, but also in the pulp and paper industry. So the digestion process is a biochemical process that breaks down the organic materials, so which is mainly used to produce biogas, and digestate, which is mainly involved in biogas plants. So the feedstocks there could be biomass, could be organic domestic waste, could be manure, sludges. So and this process is mainly particularly suited for biomass feedstocks with high water contents. This sector emits significant quantities of bio-CO2 that remain unexploited, and especially for instance in biogas upgrading plants where bio-CO2 is emitted also as a byproduct. So regarding also the fermentation process, it is a biochemical process that the microorganisms break down the organic materials such as sugars and starches to produce various products, including also bioethanol. So this is the main process involved in the bioethanol industries. So the complete process involves pretreatment to break down the biomass structure, hydrolysis to produce the sugars, and finally fermentation to produce ethanol. So it is widely applied in the bioethanol industry, but also in the food and beverage industry to produce wine and beer. So this process produces relatively pure bio-CO2 stream, but due to this purity, these bio-CO2 emissions are either reused within the same industry, for instance, for carbonation, or sold to other food and beverage industries. Overall, the emissions from this sector, from the fermentation process, represent a lower percentage of the total EU bio-CO2 emissions. Now, seeing also the other aspects of the bio-CO2 value chain, we have 3 different capture methods regarding CO2, which are mainly focused on combustion processes. We have the pre-combustion capture, post-combustion capture, and oxy-combustion. In pre-combustion, you have a preconditioning of the fuel in order to produce CO2 that could be easier captured after the process. In the post-combustion, as already mentioned, we have also other components like NOx, SOx, and also nitrogen and oxygen. And in the oxy-combustion process, Within this process, the fuel is combusted using almost pure oxygen, which in the end results in a CO2 stream that is relatively easier to capture. Regarding CO2 storage, so the CO2 produced could be either contained in the off gases and stored as off gases in the gas holders within an industry. This is mainly the practice conducted in the iron and steel industry, where off gases are stored there and are either reused within the same industry or utilized in other processes. But it could also stored as a byproduct or pure CO2 after cleaning. CO2 can also be transported as a liquid via shipping, with trucks, with rail, and also as a supercritical fluid with via pipelines. So in this case, since the bio-CO2 sites could be located elsewhere other than where the methanol synthesis is conducted or where the methanol end user is, so you need to transport this CO2 to a particular location that could be then used. Also, continue with a general introduction about the potential impurities and effects of those impurities that could be contained within those bio-CO2 sources. There are different compounds and elements that could be included into those bio-CO2 streams that could harm also the methanol synthesis catalysts, but also the equipment that are used there. For instance, we have halides, hydrogen chloride, for instance, that could result into catalyst poisoning, corrosion, and also the risk of forming toxic bioproducts that could affect the operation of the system. We have siloxanes that are mainly apparent in biogas plants. It could result in the fouling of emission control systems and also to decrease the lifespan of the equipment. Oxygen, for instance, in biomass combustion processes could cause corrosion and safety issues, but also catalyst poisoning effects. Also, of course, trace elements and heavy metals, which are could be related to the used feedstock, a biomass feedstock. For example, zinc and lead that could cause corrosion and fouling problems. Also, lead and chromium, which are also hazardous to human health and the environment. So, when designing the complete bio-CO2 value chain, there has to be taken provision out of those impurities in order to protect also the catalyst and the process. Also, we have water and moisture, which can also result to catalyst deactivation due to the crystallization of the particles of the catalyst. And also in the methanol synthesis process, water can hinder the thermodynamics by shifting the reaction towards the reactant, so it could hinder the methanol yields. Sulfur-containing species are also a threat to metal surfaces through erosion and also could result into the poisoning of methanol synthesis catalyst. And finally, nitrogen species and ammonia, the NOx emissions during combustion, and they could, of course, they are, of course, toxic and corrosive to equipment, along also with ammonia in those processes. So, which sources have we actually so far investigated in this process, in this project? We have the biogas plants, biomass power plants, pulp and paper plants, bioethanol, and food and beverage industry. We have also done a first investigation about the direct air capture, and also for comparison processes, we have also studied fossil sources in order to compare them with bio-CO2 and see actually what are the challenges there and what best practice could be adopted also to the bio-CO2 sector. So since those sectors are heterogeneous and involve different upstream processes, we needed to develop a different methodology in order to address those, in order to compare and assess those bio-CO2 sectors. For instance, the aspects that we studied are related to the total sector CO2 emissions. So which are the total emissions of each bio-CO2 sector in Europe and its contribution to the overall emissions. So this value will provide an indication about which sectors are contributing the most to the EU bio-CO2 emissions and assess the impact that we can achieve by utilizing those bio-CO2 for methanol. A second very important aspect is the CO2 concentration in the stream. So how much CO2 is contained in those of gases, which also depends on the upstream process and the feedstock composition. For instance, higher CO2, of course, indicates that more CO2 can be utilized for methanol synthesis, and we have also, in the end, lower costs per capture CO2. A seasonality aspect is also very important because certain bioprocesses can operate in certain periods of the year, for instance, wine fermentation, and or for instance, biomass combustion, which is used for district heating because the heating season is within certain periods within the year. The seasonality is also very important for biomass logistics. Also, the potential impurities. So which are the impurities and the other compounds that are included in the stream and which could affect the synthesis catalyst, and also the relevant equipment that are applied there. So in order to clean the bio-CO2 that will be eventually used for methanol synthesis in order to protect the catalyst. Very important is also the current uses of the bio-CO2. So the bio-CO2, it could be stored, it could be reused in other applications, for instance, within the bioethanol industry or the food and beverage industry, or it could be released to the atmosphere. Very important is also the bio-CO2 emission points within the plant. So bio-CO2 could be also emitted at different points within a particular plant. For instance, in biogas plants, CO2 could be produced, also could be included within the biogas stream, could be also included in high concentrations in biogas upgrading plants. And also in other processes where biogas is combusted to generate electricity or heat, the CO2 concentration there is lower. So there could be different points of CO2 emissions within a particular sector. And also very important is the geographical distribution and the emissions per plant. So those plants could be geographically distributed across different locations, and each sector could have different CO2 emissions per plant. So higher emissions with lower emissions per plant indicates a more decentralized nature of the sector. So it would be different, it would be challenging to achieve economies of scale there. And this is very, let's say, in comparison with fossil industries, this is also a characteristic of the bio-CO2 sector. So starting now with the biogas and biogas upgrading plants. So the total emissions, as we have actually reviewed the available data, would range from approximately 24 megatons of bio-CO2 per year. And the purity of the CO2 could range from 25 to 50% within the biogas, but it is also it is almost pure in processes that involve biogas upgrading plants. There are different emission points, as we also mentioned earlier. So from what we've seen, a very feasible aspect is utilizing the bio-CO2 after the biogas upgrading process, which is almost pure. But the other processes involved also capturing it after the CHP unit or in biohydrogen production unit, which are, let's say, less frequent applied processes there. So the distribution of the emissions in biogas plants, in general, there are small emissions per plant, and there is a large geographical distribution since biogas plants, due to odor issues, for instance, they are located in the countryside. So there there need to be those bio CO2 should be transported to a location or utilized on site, but it will be difficult to achieve economies of scale within one biogas plant, for instance. And the current uses of this bio CO2, for instance, after the biogas upgrading sector, it is mainly released to the atmosphere. And the seasonality in the sector is related to the used feedstock, but in general, biogas plants apply feedstock flexibility in order to achieve constant production rates throughout the year. So on the picture on the right, we have a distribution of the biogas upgrading plants, a map from the Joint Research Center. So you can see different biomethane plants in the EU. So a potential integration option of CO2, you can see on the left side the block diagram of integrating methanol synthesis within a biogas upgrading plant where CO2 could be used, captured, stored, cleaned, and then used in the methanol synthesis process. And as we also mentioned earlier, there are different impurities that could be included there. For instance, nitrogen and other elements. Hydrogen sulfide is a very important element that is included in biogas plants, but also siloxanes and halogens, which also could harm the used equipment and also the catalyst of methanol synthesis. Regarding now, continue with the biomass power plants, there's a large distribution in the available data from what we've seen in literature. So it could range from 220 to 310 megatons of bio CO2 per year. So the emission points there is post-combustion, but as already mentioned, the purity of the bio CO2 could be approximately up to 12%, in some cases more or less, but it is more, the CO2 there is more diluted compared to other sectors. There is also large distributions in terms of the emission amounts per plant. There is also a large geographical distribution. The current CO2 uses there, it's mainly also released to the atmosphere. And the seasonality aspects there are related to the used feedstock, but also the operational use. For instance, for district heating, which is related to the heating season in its location. The integration of methanol synthesis there, for instance, after combustion, CO2 should be captured, stored, also cleaned, and then used in the methanol synthesis plant. There we have also the impurities that could be NOx, sulfur dioxides, heavy metals, dust, and other compounds that could also be taken provision of when using it within the methanol synthesis process. Pulp and paper plants, we have also, is also a sector that is largely contributed to the total bio CO2 emissions. So the total emissions are around 90 megatons per year, bio CO2 per year. The emission points there could be also post-combustion. So the combustion process is also a process there that is mainly the main, let's say, factor in affecting the emissions within the pulp and paper industry. So we have the lime kiln, the recovery boilers, power boilers that are emitting bio CO2 and are using also different kind of bio feedstocks, which are also emitting bio CO2 that could be eventually used in our case. As you will see also in the table, are different CO2 concentration ranges that could be are emitted from those points in the plant. We have also the distribution. There's also large geographical distribution of the sector, but mostly most of the plants are located in Scandinavia. Sweden, for instance, has a large industry of pulp and paper. There are also no fixed, let's say, uses of this bio-CO2, and there are also no strong variations expected due to seasonality issues in this sector. In the map, you can see the pulp and paper plants on the left side, and also the timber industries that are affiliated to the pulp and paper plants, and which is also a map by the Joint Research Center about the bio-based industries. So in the next slide, there is also a potential integration proposal for integrating CO2 methanol synthesis from bio-CO2 from these sectors. And also as in comparison also with the combustion plants, biomass combustion plants, we have also nitrogen oxides, sulfur oxides, and also other compounds that could be related also to the upstream process and also to the used feedstock in those processes. Bioethanol plants are, let's say, the total emissions are not, let's say, contributing to the total emissions of the EU in a large extent. For instance, the total emissions are estimated at approximately 4.2 megatons per year, and the emission points are after fermentation. So the purity in those streams, it's very high. Could be from 99 to 100% volumetric CO2, but the emissions per plant are small, and there is a large also geographical distribution of those plants. So in this case, due to these small emissions per plant, the achieving higher economies of scale would be also challenging in terms also of the CO2 logistics aspects. The current CO2 uses in the bioethanol plants, this CO2 is mainly used in food and beverage industry, or could be also used in the pharmaceuticals industry. And there are also no strong variations expected there due to the feedstock or the process operation of the sector. So, and also in the map, you can see the sugar and starch industry in the EU, which is also related to the bioethanol sector. Also in this case, CO2 could also be used due to its high purity. It could be integrated within methanol synthesis process to produce methanol. And finally, also the food and beverage industry. So it is also mainly the beverage industry. It is also contributing, has not a large contribution to the total CO2 emissions. The processes there are also is also fermentation process, for instance, regarding the wine and beer producing sectors. And we have also small emissions per plant and also a large geographical distribution of those sectors. The CO2 there that is produced there can be reused within the industry. It could be sold to other food and beverage industries, but it could also release to the atmosphere. And the seasonality is also related to the used feedstock, but also related to the end product, for instance, wine and beer, which the fermentation process and for instance also the grape harvesting season could differ. Finally, we also included the first, let's say, outline of direct air capture. The solution, since most capture plants can capture up to 90% of the emissions, so the remaining CO2 could eventually enter the atmosphere. So And the direct air capture systems, they could also employ various sorbents to capture CO2 from the atmosphere. So it can also be applied theoretically anywhere. So in terms of the bio CO2, which is also has the location aspect, which is very critical in this case. So the direct air capture could also provide a solution here. So the CO2 that is produced there is pure up to 95%, and then the CO2 can be stored underground, can be utilized for other chemicals and fuels, such as methanol. But there are also challenges there. There are high energy consumptions and costs for the direct air capture, but there are also the large-scale direct air capture implementation up to now is limited. But we have some very interesting examples, for instance, in Iceland, where there is a direct air capture plant that captures up to 4,000 tons of CO2 per year, which could also, let's say, provide some more solutions in this sector. Going now to the conclusion and discussions. As we have seen, the bio-CO2 sector represents a very highly distributed sectors in terms of emissions, compositions, locations of the bio-CO2 that is emitted there. The biogas sector is promising, and especially the biogas upgrading plants, because the bio-CO2 there is almost pure. But the biogas plant locations, they are dispersed. It could affect the logistics of the methanol synthesis units. Biomass power plants and pulp and paper are less distributed. There are large bio-CO2 emitters, but the CO2 stream there is highly diluted. And it will, of course, require the application of CO2 capture technologies that could also, due to also the purity of the CO2 stream, could also be affected by the costs. The fermentation-related sectors, such as the bioethanol and the food and beverage industries, they produce a highly pure bio-CO2 stream, but in certain cases, this stream is reused within the same industry or sold as a market product. So this could highlight a lower potential for using this bio-CO2 for methanol synthesis. And of course, very important, the biomass feedstock impurities. They are very critical aspect in the composition, and they could exist in different forms and compounds, and they eventually could harm the methanol synthesis catalyst. So in this case, you need to also clean the bio-CO2 stream that will be used for methanol synthesis. So overall, some considerations about the bio-CO2 to methanol value chain. Very important is the location of the plants. So the CO2 emission plants, where the hydrogen production plant is located, the methanol synthesis plant, and the end user, which in this case is located within ports. Geographic dispersion of the plants, and also the emissions per plant. Very important is also the cost and the feasibility of applying CO2 capture technologies. So in order to achieve economies of scale, and the CO2 purity can affect also the application of the CO2 capture technologies. Impurities in the bio-CO2 streams, as we also mentioned, we have to clean the gas before the synthesis. The CO2 content in the stream can affect the partial pressures and the stoichiometric number in the methanol synthesis process. This means higher hydrogen requirements and higher costs for electrolyzer, higher costs and the electrolyzer capacity is required to produce the same amount of methanol. And also, what you also need to take into account is the end user requirements. What are the impurities and compositions of the methanol that will be eventually used in the ship engine, and to what extent should you purify the methanol product before inserting it into the vessel. So some next steps in this work, which is of course ongoing within the M²ARE project. Actually, there will be actual sampling campaigns within bio-CO2 producing sites to analyze the composition, the impurities of those streams. There will be a design and optimization of the methanol synthesis value chain involving the aspects that we included and we discussed previously, and also techno-economic and the environmental analysis, which is also a critical aspect in this work. So I want to thank you all for participating into this webinar. In case there are any questions, feel free to send us an email, and of course we can discuss in more detail about the presentation and some aspects that would be interesting to you.
Okay, so thank you very much,
Thank you.
Michael and Herrick, for your great presentations. So we have, I think, enough time for answering the questions. So the first one is from Moritz. I think it's regarding the slides on the biogas that you presented, Michael. So for biogas, is the 24 megatons produced including the impurities or pure CO2?
This
is
is
the question.
This is pure CO2.
Pure CO2. All right. All right. So the same from Moritz. We have another question. So, but I think you should also in your last slides, that will be one of the next steps of the project. I don't know if there is any chance to give some insight for it. So for the project, did you also make an assessment for the total emission economically feasible for the carbon capture?
Within the project, we're going to make a detailed techno-economic analysis of applying methanol synthesis using this bio-CO2 at different scales and in different sectors. So the carbon capture aspect will be covered there. So this is an ongoing work right now.
Right. Yeah, thank you. So another one from David about biomethane in particular. So he's asking why the map on your slides does not show the numerous units existing in France. Is it because the volume per unit of potential CO2 producing is too small?
This is something I must check. Actually, these data were taken from the European Commission database from the Joint Research Center. So we have to see which biomethane plants are included there. But this is something that we will need to, let's say, I will need to check within the website.
Yeah, sure. Something to be, yeah, investigated. All right. So another one from Amy, are the databases that you used available? And from what level of CO2 emissions did you consider carbon capture interesting or feasible?
The databases that we all used are from different, from official, let's say, organizations like the European Biogas Association that has, let's say, biogas plants there that are registered there. So the estimations are from them. So all the data that we use there are widely available from open source databases. And the second part of the question is also very interesting to us, because the feasibility in terms of applying the CO2 utilization is something that is currently ongoing. So applying also different scales, different purities. So let's say the relative location of the different section of the value chain are also very important. So in the end, the methanol product, apart from the level of the CO2 emissions, we'll also have to include the logistics aspect, the location of the different sectors, what will be included, for instance, to transport the CO2 or the methanol eventually. So this will be also investigated in the next in the techno-economic analysis.
All right. Seems very interesting. Thank you very much, Michael. So we have another question from Diogo. What are the main characteristics of the reactor to produce methanol? And so, for example, operating temperature, pressure, and the reaction type.
Yes, so I can answer this.
Yeah,
So
yeah,
we
sure.
use a fixed bed reactor with catalyst pellets, and so the operating temperatures are between 220 and 260 degrees Celsius, and the pressure is anywhere between I would say 60 and 90 bars. So the wide ranges then, of course, also depend on the composition, for example, how many inerts we have, and also on the specific process setup.
All right, thank you very much, Herrick. I think we'll have enough time to answer just a few more questions. We have one more from Ankit. Will you also be considering oxygen combustion of the biomass for larger emitters like biomass power plant, considering that you have oxygen from the electrolyzer? I don't know if Michael or Herrick wants to answer.
I can also answer.
Yeah, sure.
Yes, in this case, we are investigating actual plants that are emitting CO2, and but the oxy-combustion process is a very interesting process in terms of producing CO2 that could be also utilized further. So the capture after an oxy-combustion process is, let's say, simpler compared to other sectors. So they also coupling the oxygen from electrolyzers could be a very interesting concept there. So this is also, so as far as I know, this is very interesting also in other projects that are investigating this integration issues of electrolyzers with existing processes. So the oxygen, there is a large discussion there in terms of utilizing the oxygen from the electrolysis, because it is a byproduct that could also have some a market value. So it could be also used in the oxy-fuel combustion process. Yeah, Giacomo, I think you're muted.
Sorry. So thank you very much. We have another one. So Ralph Uwe is asking, are there any intents to reduce the methanol reactor pressure? So do you see any potential cost benefits in reducing the reaction process pressure?
Yes, so generally, of course, it would be cheaper to not compress to such pressures. But of course, there it depends on the catalyst that we are using. So where the catalyst then has the highest activity, and here we are not doing any catalyst development. So we're using commercial catalyst in this project from Clariant, who are also a member of the advisory board of the project. And so there we look, of course, close to the optimal conditions for the catalyst.
All right. Thank you very much, Herrick.
If I may also add, a very important aspect, apart from the pressure in terms of cost, is the hydrogen production cost. So this is let's say, also a very important aspect there. So in order to produce methanol with let's say the lowest with an optimized stoichiometric number of hydrogen addition. So in this case, hydrogen is also very important in terms of the costs.
Yeah, okay. Thank you, Michael, for adding this information. I think we can go with another one, and if we have some space left, maybe also another one more. So Joseph is asking, in general, are you concerned about the availability of biogenic CO2? And which countries are in the process of organizing themselves to make it available? So infrastructures, standards, incentives.
In terms of the availability of the biogenic CO2, based on our calculations, in terms of using this bio-CO2 for the methanol synthesis sector, so we need to, let's say, make also a reality check about how much bio-CO2 is actually captured today. So there's a very small amount captured of bio-CO2 today globally, which is also mainly derived from the bioethanol industry. So in this industry, they are mainly reusing this bio-CO2 within the same process or within other industries. So in this case, from what we have seen is that there is an amount of bio-CO2 available, but these are the aspects that you need to take into account in terms to make it also feasible in order to use this for methanol synthesis. So theoretically, there is available CO2 amount. There is no, from what we've seen, using this bio-CO2 could, let's say, produce methanol that could be also used in the maritime sector. But let's say the different, let's say the heterogeneous characteristics of this sector make it, let's say, more challenging compared to the fossil-based industry.
Okay, thank you, Michael. I think we can go for the last one. So it's from Andreas. What quantity of biomethanol could be produced, and what share could biomethanol have in the maritime sector? So also connecting to another one, it's interesting also to know, is there enough bio-CO2 to cover the demands of the EU shipping industry? So, yeah.
So in terms of the, let's say, the theoretical amount of what we have, let's say, seen from data that are available. So let's say if you would be able to capture 10% of this bio-CO2, you could, let's say, cover 4 to 5% of the total EU maritime energy needs. But of course, if you'll be able to capture 10% of this bio-CO2 that we found, you can cover some of those demands. But of course, you need to see the scales. You need to see the reality, since we're talking about a large portion of bio-CO2 being required to be captured, but you also need to see the hydrogen. So in order, let's say, to use this 10% that we've seen, you need to install 20 to 30 gigawatts of electrolyzers to use this bio-CO2. So there is also another restriction there. You have also the hydrogen restriction there. And you also need to see this restriction in terms of also the targets that EU is setting within the years. For instance, by 2030, hydrogen, there will be 10 megatons of hydrogen targeted to be produced within the EU. So you cannot, let's say that I will replace a certain percent of the maritime energy needs without taking also into account the, let's say, the targets regarding hydrogen in this case. And of course, the costs are very, very important there, because due to the different, let's say, purities and compositions and amounts within each sector, the capture cost per ton could vary a lot. With bioethanol, for instance, that has high purity, it can, let's say, be less expensive, but in other let's say, processes that involve CO2, which is less diluted, could also be more costly.
Also, to complement, maybe it's also interesting. It will be interesting to see how other industries react. So, for example, the aviation industry, if they're the route from biogenic CO2 plus hydrogen to SAF at the end will be interesting. So there, then of course there will be it will be difficult to assign then or to understand how much CO2 and hydrogen will be used for which industries. And of course, the total amount is at the end limited. And there, the questions that Michael raised regarding the cost will be crucial.
All right. Yeah. Thank you very much to you both for your answer. I think we don't have so much time for another question, so I think we can close the webinar. So thank you very much, Michael and Eric, for your very interesting presentations. So as I mentioned at the beginning, the webinar was recorded and will be available on the YouTube channel of the project. In the chat box, I left the 2 links useful to know more about the project and stay updated with the news, LinkedIn page and project website. So thank you very much also to all the audience for participating to this webinar. It was great to see so much interaction and interest on this topic. So thank you very much, and I wish you all a very nice week. Thank you.